All right, today we are going to continue looking at circuits, and we are going to discuss Kirchhoff's laws and also discuss how to approach analyzing circuits when we cannot reduce the circuit with equivalent resistance values. So to start, I've just got Kirchhoff's laws or rules listed here directly from the textbook. We've been using them for the last few days now, so this isn't anything new. The Kirchhoff's rules are the junction rule, current in equals current out of a junction, and the voltage increases and decreases when you go around a loop add up to 0. So those are Kirchhoff's laws, and when you combine Kirchhoff's laws with Ohm's law, then essentially we're using those three tools to analyze all of our circuits. And so I've got the general approach for circuit analysis highlighted in this next circuit that I've got drawn. So right here, I've got a 12-volt battery hooked up in series with an 8 ohm resistor and a 4 ohm resistor. And so first off, the junction rule here is essentially as straightforward as it can be. There are no junctions, and so that means the current has to be the same through each of these circuit elements. And then you can leverage going around the loop. All the potential increases and decreases have to add up to 0. And then you can see in my picture, I've drawn the blue line representing, for me, the direction around the loop that I am going to travel, and write down all of the terms. And so my loop is starting at the negative terminal of the battery, so I'm starting here, and then I'm going to go through the battery first. And so you can see over here, I've written down plus 12 volts. The next thing, after I get through the battery, the next thing I get to is this 8 ohm resistor. And so as I travel through the 8 ohm resistor, that corresponds to a voltage drop of I times R. So that's the I in the 8 ohm with the negative sign, with the minus sign. Then I get to the 4 ohm resistor and cross that, and I get another voltage drop. So minus I times 4 ohms, and then I just do the algebra and end up with the current through the battery is 1 amp. It's also the current through the 8 ohm resistor. It's also the current through the 4 ohm resistor. And so a typical question that might get asked in a circuit like this would be, which of these resistors dissipates the most power? How much power is generated by the battery? So not only finding the current in each of the elements, but then connecting that to something like the power and generated or dissipated. So as I was going around the circuit, you'll notice that I had sort of adopted conventions. So let's focus down here at the bottom here. When I went through the battery to start, I traveled in my loop from the negative terminal to the positive terminal, and the convention here is that we adopt is that that corresponds to a voltage increase. So that will be plus whatever that battery voltage is. If we traveled through our loop in the other direction, and you can do this because the directions that you pick are completely arbitrary, right? That's one of the wonderful things about circuit analysis is you can choose your current to be whatever direction you want it to be, and you can go around your loops in whatever direction you want. So if we had gone the other direction, then from the positive terminal to the negative terminal, then that corresponds to a voltage decrease, which I think makes sense. Now, at the top, the convention is if we travel around our loop and we pass across a resistor in the same direction as the current that we've drawn, then that corresponds to a voltage drop of minus IR using Ohm's law. If the direction we're going around the loop causes us to go in the opposite direction of the current we've drawn, then that corresponds to a voltage increase, so plus IR, right? And so these are the conventions that we adopt as you go around your loops for your circuit analysis. And again, the key here is that the current direction is completely arbitrary. You get to pick that direction. And the loop direction is completely arbitrary. You get to pick that. As long as you're true to these two convention choices here, right, and you're consistent, everyone will get the same answer when analyzing the same circuit. All right, now to demonstrate how to leverage our three rules to analyze circuits, I'm going to analyze this circuit that is provided in the textbook. And this is a circuit that cannot be reduced by way of finding equivalent resistances for series resistors and parallel resistors. The fact that we have two batteries here essentially prevents us from reducing down the circuit like we could in previous examples, right? So finding an equivalent resistance is not an option. And so what is always an option is leveraging the junction rule, the loop, the voltage drops across a loop rule, and also Ohm's law, right? So those three are always applicable, and so that's what we're going to have to fall back on to analyze this circuit. There's a lot going on here because the book had some stuff already drawn, and I added in my loops already, but the basic circuit here, we've got a battery that's connected in series to this resistor. Then we've got a junction, and down one path we just have a resistor, and on the other branch we've got two resistors in series and then a battery. Right, so that's what we've got going on in this circuit. Now, the first step in circuit analysis, particularly in a case like this where you can't do any real reduction, clearly you could combine these two resistors into 7 ohm resistor, but we're just going to leave them separate for now. The first thing you do, the first step, is pick a junction and define the currents in your problem. All right, so the book already picked the junction, so I'm going to use the same one. Junction B here, you've got 3 branches. And so, again, this is completely arbitrary, but you need to pick the directions of the current in those 3 branches and then write out the expression that relates the currents in each of those branches. And so in this particular case, the book already chose the directions, so I'm writing down the algebraic expression, but there's nothing special about that choice. Could have been anything, right? But the book has already chosen it, so I'm going to use what they've used. If you see here, I've got I1 coming into the junction, and then I3 and I2 coming out, right? So algebraically, that's just simply I1 equals I2 plus I3. So that's my starting point, right? That is one of the equations I'm going to have to use to analyze this circuit. And again, there's no wrong way to choose your currents. A lot of times there are hints in the circuit as to which direction the current is actually flowing, but it's completely arbitrary. It doesn't matter. The only thing I will say is that you choose your directions here and you do the algebra and analyze the circuit. If at the end you get a negative value for one of your currents, what that means is that you just picked the wrong direction to start, and that say if our current I3 comes out negative here, well, if it comes out negative, it just means that that arrow should have really been drawn going into the junction rather than coming out, right? So I think in this example, we'll actually see that play out. So step 1, pick a junction, define your currents. All right, we've done that. What's step 2? Step 2 is pick 2 loops. In this case, 2 loops, because we've got, this is what's known as a 2-loop circuit. Pick any 2 loops and to go around. So pick the directions that you're going to be going around those loops. And so you can see I've done that already. My loop 1 is the left loop, and my loop 2 is the right loop. Of course, there is a 3rd loop, right? You could choose to go around the perimeter, of this circuit in this direction. You could do that. That would be our loop 3. The point is that here there are 3 different loops you can choose. Only 2 of them, right, any 2 that you choose, are needed to actually analyze the circuit. The 3rd loop just provides essentially redundant information. So pick whatever 2 loops you want to use, and then you're off to start doing the analysis. All right, so I've got my 2 loops chosen. I've got my directions that I'm going to travel around those loops chosen, and now I'm going to get started. So get started, what does that mean? Well, really it just means I'm going to go around loop. So loop 1, I go through battery 1, then I go through battery 1, then I go through R1 in the same direction as I've chosen I1, so that's a minus I1 R1. Then I get to the junction and go down the middle branch, and I go through R2, and I'm going in the same direction as I've chosen the I2 current, so that's also a minus I2 R2. Then I get to the junction down at the bottom, and I basically complete the loop. So this is the full expression here of traveling around loop 1. Now for loop 2. Well, loop 2, the first thing I do is I go through the battery, V2. Notice I'm going in the direction that goes from positive to negative, so that actually corresponds to a minus V2. That actually corresponds to a voltage drop as I go through the battery in that direction. Then I travel through R2. I travel through that middle resistor in the middle branch. I'm traveling through that resistor, though, in the opposite direction as I2 that I've drawn, and so this turns out to be a positive I2 R2. Then I hit up this junction B, and I go through the right branch. I go through resistor R3, and that I'm going from left to right, so that's the same direction as I3, so I get a minus I3 R3. And then I go through the R4 resistor, again in the same direction as I3, so that's a minus sign. So I haven't done anything particularly fancy. All I've done is I've chosen my loops, and I've traveled around the loops, writing down basically plus or minus delta V. Right, that's the only thing I've done. Or I guess really plus delta V, which sometimes is positive and sometimes is negative. So I am going to combine, after I get rid of some of these marks, I'm going to combine my 2 loop expressions with my junction rule to solve for the currents in each of the circuit elements. So notice what I've got here. I've got 3 equations, and I've got, in this problem, I know all of the battery voltages and I know all of the resistor values. So I've got I1 as an unknown, I've got I2 as an unknown, and I've got I3 as an unknown. And so when you look at just these two expressions, right, that is not enough information to solve for three variables, and that's why we need this third expression. So I've got three equations and three unknowns here, and so the first thing that I'm going to do is I'm going to substitute out my junction expression, or substitute in my junction expression. So over here, right, I know that I1 equals I2 plus I3, and so if we look over at the terms, I only have I1 right here, so I'm going to immediately substitute that out, so I get two equations with two unknowns, and so that's what's happened here. I've just rewritten equations 1 and 2 with all of the battery and resistor values, and with the substitution of I1 for I2 plus I3. All right, so I've made that substitution. Now I've got two equations and two unknowns. And so all I'm going to do in this next step, so to come down here, all I'm going to do is a little bit of algebra. So I have separated the I2 and I3 values and then combined the I2 values together over here. So I have I2 times 6 ohms rather than two separate minus I2 3 ohms. And then down here, I've essentially done the same thing. I've added together the minus I3 terms, right? I had a 3 ohm and a 4 ohm term, and so those add together for 7 ohms. All right, so now I've got my two equations and two unknowns in about as simple of a form as I can get them, and at this point there's a variety of ways that you can finish the algebra. Again, the goal here is to get one equation and one unknown, and you can do that a variety of ways. What I'm going to do is I'm going to add equation 1 to 2 times equation 2. And you'll see why I want to do that once I set this up. So equation 1, just rewriting that, and then 2 times equation 2, I've written out just multiplying each term by 2, so I get minus 58 volts, I get plus I2 6 ohms, and then I get minus I3 14 ohms. And so it should be apparent that if I add these two expressions together, right, so that's basically going to be, I'm adding those two terms together. Let's make this smaller. I'm going to add those two terms together. That's going to give me minus 34 volts. I'm going to add I2 6 ohms and minus I2 6 ohms together. Well, that's going to give me 0. And then I'm going to add I3 3 ohms and I3 14 ohms. So that gives me minus I3 17 ohm. And then I can immediately solve that for I3, and I get 2 amps. Negative 2 amps, excuse me. And remember, that negative sign, as I mentioned, just means that when I picked my directions for the current initially, I just chose the wrong direction for I3. So if I was going to sort of answer a question related to what is the current through that third branch, I would say, all right, I got minus 2 amps, so that means, looking back up at this picture, it wouldn't be 2 amps in the direction chosen, but it would be 3 amps this way. Or, sorry, 2 amps this way. All right, so you would just clarify that when you go to report what the current value is. All right, so I3 is minus 2 amps. Now we just go back to our expressions. I1 relates I2 and I3, so I'm going to plug in my minus 2 amps. into my expression. You can see I've done that right here. And then just complete the algebraic steps, and I get that I2 has to be 5 amps. And then lastly, I just go back to the junction rule. And I can immediately solve for I1, and I get plus 3 amps. So both I2 and I1 come out as positive values, and so that means the directions I chose at the start were the correct directions, and only I3 was in the wrong direction. And so once you know all of the current values, then you can start answering questions like how much power is dissipated by each of the resistors, how much power is generated by each of the batteries. Keep in mind that the current through V2 is actually going this way, right? So you will get both that battery 1 and battery 2 generate power, and that power would be equal to, for the battery, the power will be I times really the EMF, but in this case, it'll be the voltage value given. And then for each of the resistors, the power dissipated will be, well, it's either I times delta V or I squared R or delta V squared over R, right? Any of those three will give you the same value for the power dissipated for each of those individual resistors. And again, we needed to do this circuit analysis to figure out what the current is through each of the elements. Now, of course, if you add up all of the power generated by the batteries and compare that to all the power dissipated by the resistors, what you'll get is that all of that adds up to 0, right? All of the power generated is dissipated in the circuit. And that really is the extent of the circuit analysis for our circuits, really any combination of batteries and resistors. This is the approach, just leveraging Kirchhoff's laws. So the basic idea here is that if you can reduce the circuit by finding equivalent resistance, you go with that approach and find the current through the battery, and then go back through using junction rule and find the current through every element. In this case, and in other cases that you're going to look at, the circuit is complex enough that you cannot reduce it down, and then you need to use just the Kirchhoff's rules, junction rule, loop rule, and Ohm's law, and you can analyze every circuit. You can even use that approach on circuits that could be reduced down to an equivalent resistance. This approach right here, this step 1, this step 2, and then do the algebra, that will work on all of our battery and resistor circuits.